All right, so first lesson for chapter 21, which is going to be about nuclear chemistry. Okay, so we're going to talk about all different aspects of nuclear chemistry. This is our final chapter. There's 4 lessons. 2 are a little bit longer, and the last 2 are shorter, so they're combined into a single day. But we are almost there. We can see the light at the end of the tunnel, so just keep up what you are doing, and summer will be here for you soon. So first we're going to talk about types of nuclear particles. Okay, we're going to have 5 different types of particles. One of them is going to be an energy ray beam, so a little bit different. So a nuclear reaction involves the conversion of one type of atom into another. So usually it's something heavier into something lighter. Or it can convert into an isotope of the first. So we could go from like carbon to carbon, but they're different isotopes. And remember, review the isotope definition if you can't remember. While giving off a nuclear elementary particle, which is what we're going to talk about, these different types. So just as a review, in the symbol, argon 18 and 30, what do the 30 and the 18 stand for? And so hopefully you remember that this is the atomic number. This is the number that never changes on the periodic table. It is the number of protons and the number of electrons in a neutral molecule. Okay, or no, that should say a neutral atom. Now, protons, it's always going to be equal to that number. But electrons, because they can be gained and taken away, that's the number that can be different if it's an ion. The number on top, this is the atomic mass. This is going to be the number of protons plus the number of neutrons. And so hopefully you remember my shorthanding of the protons, the electrons, and the neutrons. And so this is how we distinguish our isotopes. Okay, so if you don't remember that still, make sure you go back and review. All right, so these are the following elementary particles that we're going to need to know. This first one is not really new to us. This is a proton, otherwise called a hydrogen. Okay, so we called it a proton. It's going to have one proton and a mass of 1. The second one is a neutron. Neutrons have no protons, no electrons, hence the 0. And it's going to have a mass of 1 because it has 1 neutron. The next one, I hope you can see the trend. This is an electron. It has 1 electron, which has a negative charge. And electrons have negligible mass, and so we're going to write that to be 0, because if a neutron or proton weighs 1, the electron in relation to that is 0.00055. So it's essentially nothing. But this is also going to be called a beta. Let's make this like a beta fish, a beta particle. And that's what this symbolizes right there. So 1 electron is equal to a beta particle. The next one is called a positron. It is a positive electron. So it's like a Brangelina name. It's a positive electron which still has no mass. And so this is going to be called an anti-electron. Okay. The next symbol here, hopefully you recognize this to be helium. But it's also going to be an alpha particle. An alpha particle is made up of 2 protons, 2 electrons, and its atomic mass is 4, which means 2 protons and 2 neutrons. Now, I said earlier we were going to have 5 particles and then like a 6th one, which would be weird, and that's this last one right here. And this should be 0, 0. The way that this is written looks strange, but this is gamma. And so this is not a particle, really. It's a gamma ray, which is on the electromagnetic spectrum, along with X-rays and infrared rays. The gamma ray is off there in that very high energy area. Okay? So you need to know these. Okay, make sure you know them and you can identify them. All right, so now we're going to talk about balancing chemical nuclear reactions, and then we're going to take a break and do the second part of the video. So to balance the nuclear reactions, we have to balance the following. We have to conserve the total number of protons plus neutrons in the products and the reactants. This is conservation of mass. And we have to make sure the nuclear charges in the products and the reactants are the same, and this is conservation of atomic number. So what this really means is everything on top must be equal and everything on bottom must be equal, because the top is mass and the bottom numbers are atomic number. The bottom numbers are the atomic number. So the way this works is I treat this like an algebra problem. Okay. So the first thing I'm going to do is I'm going to take all the numbers on the top, and I'm going to set up an equation, and that's going to be that 212 is equal to 4 plus z. So I'm just taking 212, 4 plus z, all the way across. I'm going to rearrange it by subtracting 4 to the other side, and that tells me that z is, hold on, there we go. Z is 208. So that is the atomic mass of the unknown element X. Now I'm going to do the next one with the bottom numbers. 84 equals 2 plus Y. It's going to erase that, but I wanted that number, the underline, to go away. Okay, so now I'm going to write 84 equals 2 plus y. Y must be then 82. Now, to figure out what x is, I'm going to use the atomic number because this is the number that never changes. And the element that is element number 82 should be on your periodic table, lead. Okay. So let's do one more, and then I'll have you guys work on one and submit that separately. So, okay, this is hard to see. The plus sign is in here and over here, okay? So now we're looking for the reactant. So let's do the top numbers. Let's see if I can insert. Space. Okay. Perfect. Go away. There we go. All right. Oh, come on. There we go. Well, technical difficulties. All right. X, Y, Z. X, Y, Z. So I'm going to take the top numbers. 142 plus Z equals 142. I write them out no matter what, because I don't want to make a mistake. And this is z is equal to 0. Then I'm going to take the bottom numbers. 61 plus y equals 60. And this gives me y is equal to -1. And so now I have to put some of that information we just learned to use, and that's what x is equal to when 0 and -1 are the atomic number and the mass, and it's going to be an electron or a beta particle. Either one would be suitable because they mean the same thing. Okay, so now pause it and practice. These are so simple, but assuming that they're too simple to pause and practice is going to get you into a lot of trouble. So we're moving on. If you haven't paused and practiced, pause it now, practice it. If you paused and practiced, good for you. Let's see if you're right. So I'm going to take 253 plus 4 equals 1 plus Z. So we can see even though there's two reactants, it's not going to change the way I set up my formula. I don't know what just happened. I left out the 5 and created a whole new number. Okay, so it's not going to change, and you can choose any variables. It doesn't have to be X, Y, and Z. You could do A, B, and C, whatever you want. I hope y'all can't hear my stomach growling. Okay, so 253 plus 4 equals 1 plus z. So this is going to give me 257 plus 1, or 257 equals 1 plus z. I'm going to subtract the 1 to the other side, which gives me 256 for my atomic mass. Now I'm going to do the same thing for the bottom. 99 plus 2 equals 0 plus y. And if you're thinking to yourselves, this is so easy, there must be a trick. There is no trick. This is going to be one of the easiest things that we do here at the end of the semester. After all the electrochemistry, after all the thermochemistry, the solving for the radioactivity equations is very nice. So we're going to use the 101 to identify the who, and that's going to be MD, and that is the answer, and I hope you got that answer. So we're going to go ahead and take a break before we talk about nuclear stability and predicting the reaction types, and which will be the end of our lesson 34. So make sure you come back and finish up